.496.
496? 50%? All right, 496. But yeah, roughly 50% chance. All right. Given it's a pass. Given it's a pass. Oh, conditional probability. Liz, I agree with you too. It's like, yeah, it makes sense. This can sometimes make it complicated. So if you're able to do those two problems, like, I didn't need that formula, please don't use that. I'm being serious. Like, we understand it. Conditional probability. It's based on this condition, so it limited our what? Denominator. Like, it was only passengers. We didn't consider the what? The driver numbers. Yeah, conditional probability. Cool. Hey, in my next problem, it's going to deal with the cards. I especially encourage you to try this problem with the cards without looking at that.
Okay.
I think, this is my opinion, is I think when people try to do this question with this, they get more complicated, they get thrown off and come up with a different answer. So I want you to just think about the actual, just keep it, like use your common sense to go, all right, logically, this is what I have, and this is what would be in the numerator, this would be in the denominator. If they say a given scenario, that means that given scenario is that denominator, right? The total number for that given scenario, right? So if they said, hey, given that people have white shoes, you're like, okay, we're only considering people that have white shoes, right?
Mm-hmm.
And that's the total number of people who have white shoes in the denominator. All right, so here's the question. Everyone? Cards. How many cards in a deck?
52.
52 cards. How many cards are red?
26.
Half the deck is red, half the deck is black. I do want to point out two red cards are the diamonds and the hearts. So we do have to have knowledge of that before we do the problem.
Mm-hmm.
The black cards are the clubs and the spades. All right, so here's my question. I'm going to select one card. What's the probability that I select a diamond from the deck? Given that, this means you know, you have knowledge of this. Given that the card is red. And I encourage us to look at this problem. We're going to answer it. It's not easy. Michael, let's ignore that. First of all, what's the given scenario?
26.
If you wanted to write it with this stuff, we can. The given scenario is the card has to be what?
Red.
Red. Well, we're looking for the probability it comes out to be a what?
Diamond.
Diamond. So am I counting any of the black cards?
No.
All right. Let's say the bottom half of the black, they're all out. They're out. Only the red cards. You want to see this? Given the card is red, so I only got red cards now. Only the red. See how it's not nearly, it's not the full deck anymore. And I'm going to come up with my fraction. This denominator is not 52 anymore, is it? What's the denominator?
26.
26, I love it. We don't need that formula over there. 26 red cards total. Because you said, given that it's red. If they told us given that it's red, it has to be red. There's no black cards in this, right? 26. Now, how many diamonds are in the deck?
13.
And we just got to remember how many diamonds there were. Do you remember in the total number of this, there were 13 of these, there were 13 of these, totaling up to the what? 26 total red cards. So the top number is going to have to be a 13. Now that's a great answer, but I think we could reduce that. What's that?
50% half.
Half, or I heard 50% or 0.5. Oh, love it. I don't, Liz, so I put a problem like that on the test. I get 25%. A lot. Yeah. I'm telling you. Yeah. Taylor, I did it. 25%. I think what happens is they try to get in here. And they get in this, and they see the P's, and it gets a little messy, and right? So I encourage you. We can still look at it. It's like, all right, that was the number of the red cards. That were the numbers that were red and diamonds. I mean, if you want to look at that photo. Number of red cards, 26. Number of red and diamonds, 13. If you want to look at it that way. Cool. Awesome. Hey, great job with that. And when I put something else on the board, if you didn't copy, go ahead and copy it now. If A and B are independent events, then the probability of A given B will simply only equal the probability of A. Now I want you to see where this came from. All I did was take this formula right here, right? And I substituted right here this part for this. It's in the book. So if that was substituted here, can you see what would cancel?
B.
So I just wanted to see why. I wonder if you're curious where this came from. Why is this true? Well, I took the probability of A and B, was there, and I divided out the what? The probability of B, and what cancels?
B.
Does someone say that? I mean, that's what's going on here. What's key is, for your notes, this one and this one both had the phrase, if A and B are independent events. This one alone, though, had no statement like that, right? So, if A and B are independent events, what has to be true? Probability of A given B must equal the probability of A. Cool? Hey, would you make a note? I know there's like 3 things that are not on that formula sheet. This is on that formula sheet, this is not. So that's something, would you remember that? Would I remember this one little key statement? I think you will. Just go, oh, it's just going to be this probability. If the events are independent, that means one's not dependent on the other. Does not depend on B. A does not depend on B. It'll just be the probability of this A occur. Cool? So I'm going to go to a problem out of the book. I'm going to do number 10 from the textbook. And it's a long statement, and all you have to do is say yes or no. But afterwards, Owen, can we explain why? All we're going to do is reference this. The question is about whether or not 2 events are independent or not. Cool? It's a long paragraph. No worries. We're just going to say yes or no. That's it. But hey, if A and B are independent, what has to be true? This probability will have to equal this probability. So here's this long word problem. We're just going to have to listen to the word problem, write keywords down. We'll make sure we'll come up with that and that. But we're going to keep it simple. We're just going to check to see if the probabilities are the same. Right? I mean, you know what I can do with this statement? I can actually reverse it and put knots on both of them. So you know what's going to go on? Is this true? If the probability, or A given B, is not equal to the probability of A, they call this a contrapositive. I don't want you to get so worried about mathematics. Have you ever heard of a contrapositive? It's where I switch these around and I'll put knots. See the if and the then? So I'll say, if probability A given B is not equal to probability A, then the events are not independent. But that's what you and I are looking at.
So they're dependent events.
Yeah, he knows they're dependent. Are not independent, as you said, dependent. There's some dependency. It depends on this. Cool? So I want to keep it simple. If these 2 numbers are not the same, the question is, are the 2 events independent? And I'll give you the 2 events for the problem. I'll read you the 2 events. Paragraphs coming up, everyone. But would you keep this problem simple? This is going to be number 10 from the textbook. It's in 5.4. This is actually on page
292.
292. Are the events independent? Yes or no? If these 2 numbers are not equal, do you agree we're going to say no? Look, to be independent, so if these 2 probabilities we get out of this problem are not equal, we're just going to flat out say what?
No.
No. All right? No, because that's really what we're saying here. If these aren't equal, then they're not independent. No, they're not independent. So here's the question. And as I read this stuff, we'll jot some stuff down. The probability that a randomly selected individual in the United States, 25 years and older, has at least a bachelor's degree is 0.279. Oh, we can abbreviate that. Want to put some notes? Probability, bachelor's degree, 0.279. You can write, the reason they said at least 25 years old, everyone, do you think like 5-year-olds have bachelor's degrees? So they looked at only a specific age and older, right? They said, let's look at 25-year-olds and older, and they said, all right, but the probability that a randomly selected individual in the U.S., 25 years and older, has at least a bachelor's degree, so they can have a PhD also, but here's the odds. Randomly selected, 25 years and older, about 28% of the population has at least a bachelor's degree. Okay, got it. Here's the next statement. I'm going to bang on the table too, so I don't want to scare you. The probability that an individual in the United States, 25 years and older, has at least a bachelor's degree, given that the individual lives in Washington, D.C., is 0.485. Okay. So probability you got the bachelor's degree, given that they live where?
DC.
Live in D.C. is actually 0.485. All right. So here, these two numbers, the only two numbers given in the problem, the two probabilities. Probability bachelor's degree, 0.279. Probability the bachelor's degree lives in Washington, given that they live in Washington, D.C., 48.5%. All right. What's the question? Are the events having a bachelor's degree all right, what's the other event? Are the events having a bachelor's degree and the other event lives in Washington, D.C. Are these two events independent? Right? Well, if these two probabilities aren't equal, we're going to say a big flat, look, not independent. We're going to say no, right? Are they equal? No. Big ol' what? No. And would you keep it simple? Like even in the test, once you read through that long word problem, if those two probabilities are different, you're saying what? No. Everyone got that? I'll say it again. You go, these two probabilities are different? No. No. Boom. Okay. Be independent. These would have to be equal. There's some dependency here. Now, explain why. Right? I don't have to write a long paragraph. All I have to do is this. There's my theorem. I see it right there. I just have to write the probability of bachelor's degree, given that they live in Washington, D.C., is not equal to this probability. There's my explanation. I don't know if I'll write explain on the next test. I used to write it. I mean, students would write like 2 pages of stuff. And I read through the two, I'm like, they still didn't state it. Because in math, you got to reference like a theorem if we're going to justify something.
Can I ask a question?
Sure.
Say probability of bachelor's degree is 0.279. And probability of bachelor's degree living in DC is also 0.279. That time, do they become the dependent?
That's a good question. I'm going to say this as a mathematician, statistician.
Uh-huh.
I still don't think we have evidence that we could truly say they're what? Independent. We're saying it here in this theorem.
Uh-huh.
We're still saying, there could be just chance that they came out the same and stuff. But yeah, you could assume that there is, independence there.
Well,
Hey, I was wondering if someone knows why. Why did this jump so high? DC, why DC?
it's more money.
Well, what's going on in DC? There's a lot of what kind of jobs? Think
Federal-
DC, think
federal-
Northern Virginia, what is it?
Federal jobs,
Yeah,
government.
federal government. That's why, that's why so you go, what's going on here? Right, it's all these government jobs. So we're saying here, probably you have a bachelor's that, given that you live in DC, well, there's so many government jobs, and that's why that's so high. Cool. Hey, last thing we're doing is have a little fun. Oh, question, go ahead.
Could it also be higher because it's like they're making the sample space smaller? Because like when you were saying about the left hand side, it was gonna be, what did you say, it was gonna be higher or lower?
Yeah, I got you.
Small group of
Yep, with a
people.
small group.
Yeah.
Yes, funny thing, in small samples, anything can happen.
Right.
Anything, but then as you get towards the what? Large and large, it's gonna go towards that. You're exactly right.
Okay.
The law of large
I mean,
numbers.
I get what you were saying about like the federal, but I just didn't know if that was something to do too.
Cool.
Okay.
Very good. Hey, last thing, and we're just gonna have, it's only gonna take a second. How many got here? How many total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 23. And when we're gonna look at the probability that 2 people will have the same birthday. Cool? All right. I'm gonna say at least 2. Last problem. Share a birthday. This will only take a second or one. But this is my favorite problem. They call this the birthday paradox, probability problem, because it is a paradox. I mean, how many days in a year? We won't consider leap year, even though it's leap year. How many days in a year? 300 what?
65.
65. And right now we got about like 23 people. We got roughly 23 people. So you might be thinking the odds that at least 2 people share a birthday. Not to be the same year, just the same day, but you know, we might think, oh, it's just probably this, right? No, it's way higher than this. And we're gonna find out right now. First of all, see the at least 2? Well, I'm using the Complement rule. One minus probably that no 2 people shares a birthday. Okay. Like I said, I'm not gonna keep you up. This won't take that long. 1 minus probably no one shares a birthday. That's how we're gonna attack this. Cool? Now, here I'm gonna start out. Everyone, what if there's 1 person in the room? Well, there's a 100% chance that no one shares a birthday. Do you agree? If there's only 1 person. Well, what if there's now a second person in the room? Well, there's a really good chance that this person does not share it with this person, which is 364 out of 365. All right, that's the odds that this person does not share it with this one, right? Isn't it really good? It's like me and, all right, it's like, what's the chance if we don't share a birthday?